There's a very important mathematical property that is associated with the operators that are associated with observables. And that property is known as Hermiticity. Sometimes we simply say if an operator has this property of Hermiticity, we say that it is a Hermitian operator. Now, this is a very important property really for two reasons. One is that, as we will see as we move on in the course and try to make predictions with our theory, this mathematical feature of the operators associated with observables is very useful in those derivations, and it comes up over and over again. The second reason why it's very important is that it is the property that ensures that averages associated with our observables associated with, now I'll put in parentheses here, real observables. I mean, there are sometimes we define somewhat abstract observables, right, that might have complex numbers in them, but your typical observable doesn't, right? Your typical observable is momentum, is position. It's always a real number, and so the average of such an observable also should be real. So this is the property that ensures that those averages associated with the real observables are always real. Now, you would think that they should always end up being real, but you need your operators to have certain specific mathematical properties. Now, if you have any doubt that this is somewhat of a subtle issue, let's consider a simple example. Suppose we were to calculate the average of the momentum we would observe in a given quantum state. Now you know that that would be in the real space representation just the integral of psi star psi, right, with the operator sandwiched in between, h bar over I d by dx of psi of x integrated dx. Now, if you look at this, right, we want it to be that no matter what value you put in for your wave function, that this is always going to be a real number. You can write that like so. This is the set of real numbers. But just looking prima facie at this integral, it's not at all obvious this would always give me a real number. For example, I can imagine wave functions that are real. So then everything in this expression would be real, except I've got this divided by I. You would think many times this could turn out to be an imaginary number. But the fact of the matter is no, this will always be real. And the question is, how does that always end up being the case? What is the underlying mathematical structure that ensures that? Now, to show you what that structure is, I'm going to move along considering this particular observable of momentum because it will make our discussion more concrete. But I want you to notice that the considerations I'll be giving are completely general and would apply to any operator. So let's see how we could prove this in the case of momentum, and then we can think a little bit about whether or not it should apply for any general operator. So what we want to do is we want to show that the average of the momentum, right, which is going to be always real, and we know how to compute that average. It's psi times the momentum operator applied back to psi again, right? And I want to show that that is always real. So I just want to make my note here. We're considering P, but parts of this consideration are general. We can imagine also a general observable. Now, if I want to show that this is a real number, a very cute mathematical trick is to say, well, if it's a real number, it has no i's in it, right? There's no imaginary number involved. And one way I can ensure that is if I take my number and I flip all of the signs on any i's that might appear inside that complex number by taking the complex conjugate and then checking whether I get the same thing back again. If I get the same thing back again, it must have been a real number to start with. And I think you can see that also because in general this is a complex number in the form of a plus bi, right? And if that is going to equal its own complex conjugate, which would be a minus bi, The only way these two could be equal is if b were 0, and therefore I have only the real part a. And I'd just like you to notice that using this condition, of course, would prove things whether or not it's a momentum operator in here or any other type of operator. So much of the structure of this proof is going to be quite general. Now, you'll notice that we're thinking now about the complex conjugate of an inner product, and there's a nice mathematical feature of those I would like to remind you of. I'd like you to notice that when I take the inner product psi on phi of two wave functions, and I take the complex conjugate, that ultimately is going to be defined as the integral of psi star. And again, I could do this in any representation. The math is going to be the same. I'm just using the real space representation to show you the proof. Integral dx, right? And now, of course, I have to take the star of that. And as you guys know, when you complex conjugate something, all you have to do is go inside and flip the sign on every single I that appears anywhere. So when I do that, there's no I appearing in an integral. And likewise, there's no i's appearing in dx, but they do appear in my two functions. So I have to flip all the signs in phi, and that's easy to do. You simply take the star of phi, so that would flip all of those potential sources for an I. Likewise, I would do the star of psi star, which gives me psi back again, flipping all the signs twice on the i's. And as we said, dx star is just dx back again. There were no i's in there. And finally, I hope you can see that I've come back to another nice inner product. I, in fact, wrote the wave functions in reverse order just to emphasize that fact. This is just phi, right, inner product then with psi. So it's kind of a very nice feature, something good to always keep in your head for proofs, that if you star a Hermitian inner product, you simply just flip the order of the functions that are involved. Very good. Now, I want us to use this property. So, right, what I want you to see now is that if I can ensure that psi with p hat on psi, right, which is this quantity, right, if I can show that that equals the same thing but written with these functions in reverse order, where I put p hat psi first and psi second, right? If that is always true, then, of course, because this I know is just the star of it in reverse order, then I will have proved, in fact, that psi p hat psi would equal, if I can show this, then this is the same also as psi with the operator in the second slot, but complex conjugated, and then that is sufficient to show then that, in fact, this is a real number. So it all boils down to whether or not I can show this interesting feature, which is simply that am I always guaranteed that if I move my operator from one side of the bracket to the other, right? So instead of implying on this function, it implies on that function. If that move always gives me the same thing, then I can guarantee that my averages are always real. Now that property is actually something known as hermiticity. This follows from what's called hermiticity. Now I'll give you a more direct proof of this. But if we can prove this hermiticity condition, we're done. We've got always real observables. So let's define this. So what we're going to say for hermiticity in our definition is as follows. So there's a definition. And in this definition, what we are saying is if I can do that operation, if I have an operator on one side of an inner product, and I can ensure that the result is always the same, if I were to move that operator from one side of the inner product over to the other side of the inner product, then, if that's true for all possible functions, for all psi and phi, if that's true, then we can say that the operator O hat is Hermitian. And that the operator then has the property of hermiticity. And what we've proved then is, note, what we've shown is that for Hermitian operators, the averages are always real. So, all we need to prove so that we can ensure that this momentum always turns out, average momentum always turns out to be real, even though we have this confusing I in here, is simply to show that that momentum operator is Hermitian. Well, we can do this in two ways. First, I'm going to give you a specific computation. We can check this explicitly first, and then I will give you the general proof. But if we want to check it explicitly, what we are going to do then is to begin with the momentum operator applied to the first wave function, which then would mean the following. I would have the integral. Momentum operator is h bar over I times the derivative with respect to x, then of psi of x. That's my momentum applied to psi. To form the inner product, I then complex conjugate that and then multiply by the other wave function and integrate over all possible values of x. And now basically I want to manipulate this expression until I can move all of this operator so that it not applies to psi but applies to phi. Now some of those pieces will be easy to do because these are just constants. So let me factor out those constants first. So there would be an h bar comes out. When I pull the I out, because it's actually I star, I get this extra minus sign, which is what makes this proof at first a little bit confusing as to how it would work. Then I have the integral of the x derivative of psi, and that's of course a function of x, times phi back again, times phi of x, integrated dx. And now my only remaining job is to move the derivative from this function to the other function. And that should sound familiar to you, right? That's simply integration by parts. And here's how we can remind ourselves how that works formally. So formally speaking, I can rewrite this as h bar over I. I have an integral. Oh, I notice here a small error. When I was doing the star operation and flipping the sign on everything, there's an I here whose sign I flipped. There's no I in a derivative. It's just, take a difference and divide by delta x. But there could well be I's in psi, so I better flip all of their signs first. So this would be psi star. Now, with that corrected, I want to move my derivative over, and the formal way you can do this is to rewrite your integrand as the derivative of the product psi star times phi, right? And then subtract off. Now notice, if I were to use the product rule, this would give me the derivative of psi star times phi, which is exactly what I have, but I get this extra piece that I don't want. I will get psi star times the derivative of phi. So to compensate for that, I had better subtract that off. So I'll get psi star times d by dx of phi. And this whole integrand then will be the same as the original integrand, and then I simply integrate with respect to x. And this maneuver, of course, is known as integration by parts. Now, what makes this whole thing work is that now I have an exact derivative, and that's easy to integrate. It just gives me the function back again. So the net effect that I have now is h bar on I. I then have a sum of two terms. The first term is just my function back again, psi star phi. And it's important that we recognize that these wave functions now are evaluated at the limits of my integration, which goes over all of space. So they go from minus infinity to infinity. And then what I'm left with is the integral of the second piece, which would then be the integral of psi star of x times d by dx. I'm just putting the x's back again because the proof is almost done. I don't have to save as much writing, like so. Now, the last little bit to realize here is that my wave functions have to vanish at infinity. If I had a wave function, otherwise they won't be normalizable. If I had a wave function psi, say, that looked something like this, it has some kind of strange features maybe, and then it goes to a non-zero constant out as x goes to infinity, well, then that would mean there's a constant probability out here, and when I integrate under that probability, I would get infinity, and my wave function wouldn't be physical. It wouldn't be normalizable. So therefore, I cannot have a situation like this. What I actually must have is that my wave functions, both psi and phi, the same consideration works for both, of course, must have a feature. I don't know what they do at the beginning, but eventually they have to approach towards 0. So these limits of integration then give me 0. And then finally you can see I've got a double minus sign. So that pesky minus sign that came from the I actually goes away because of the other minus sign from the integration by parts. And I have h bar over I, the integral of psi star of x, times d by dx of phi of x, integrated with respect to x. And of course, that is simply the inner product of psi with now exactly my momentum operator, right? Because this h bar on I can be moved into the integral now right before the derivative. That then is exactly the momentum operator applied to phi. And I've managed to prove that, yes, indeed, I can take this momentum operator from this side and actually move it to the other side. So therefore, the p hat operator is Hermitian, and as I've just proved, for any Hermitian operator, that implies then that the averages computed with this operator are always real. And those averages, of course, are from doing psi, p hat psi is always real. Excellent. So, now, we can prove this in general also. This is just a worked example. So if we want a general proof, the general proof, all we need to prove is that observables give operators that are going to be Hermitian, right? So general proof that all real observables have operators that are Hermitian. Operators, or I'll just say they have a Hermitian operators. The way we would prove this would be as follows. Let's start with some general observable, O, and I will consider its action then on inside a inner product like so. My goal then is to get this where I can move the O operator to the other side of the bracket. And the trick we're going to use is we're going to use Parseval's theorem, which says we can rewrite this in any representation that we want and get the same result. And of course, the representation I want, the special representation that allows us to carry out proofs, is to go into the O representation itself. So in the O representation, I have the application of the corresponding O operator in that representation times the corresponding wave function in that representation acting on phi bar. But we've shown, actually, that in its home representation, the action of the operator O is just multiplication by O. We showed that earlier. And then at this point, I can write this out as an explicit integral. So I'll have an integral of O times the O representation star times phi bar of O dO. And I think you can see how this works. Because the observable O is always real, it will be its own star. Because see, now we're just multiplying by a constant factor, so that's pretty easy. So that then gives me integral psi bar star of O. Because I still have the star to apply to the psi bar, the O star is just O. We could even write it here, O star, but then that goes away because O is real. Because we were saying we're dealing with real observables. And then I've got phi bar of O dO. So that we can see now we have a result in the O representation of the O function times O multiplying the phi bar. But just to complete the proof, you will notice then that we are still in the O representation. So this is the same thing as the O operator in its home representation. And then finally, by Parseval's theorem, we can change this statement again back to our home representation that we were working in, perhaps the real space representation, and then this then just becomes the operator applied, as you can see, onto the other side of the inner product. So we succeeded in general in moving things over. So just to review so that the logic is clear, I've now given you a general proof that any real observable should have this property of hermiticity. We actually prove that very explicitly in the real space representation for this somewhat puzzling momentum operator. But after our general proof, this result should not have been too surprising, although it was interesting to see how it was worked out. But either way, once you establish that you have a Hermitian operator, that then tells you, as we can see here, very quickly, that then when you calculate an average, it's the same as the average with a complex conjugate on it, because that's basically the same as moving the operator to the other side, and that's what ensures that you always get real values for averages when you are dealing with physical observables. This property of hermiticity, the hermiticity of operators that correspond to actual observables, as we've said, is something we can use in other ways, and we certainly will later on in our course.